think we'll make a start. We'll just do the introduction to CIWEM, and then I'll hand over to Ludwig and Howard to talk about the micropollutants. So yeah, so going to be talking about micropollutant removing ozone to improve river health. So been doing some projects with Severn Trent on that, so it'd be good to hear about that. It's quite a popular thing in the media at the moment, so along with overflows and various other bits. Just to let you know, obviously this meeting will be recorded, so please. So yeah, webinar will be recorded, so we'll put the recordings up on the CIWEM website, YouTube, hopefully later on. If you have any technical difficulties, do let us know. Just raise your hand. So Barbara will be managing that, and myself at the end with questions and answers. So we'll be having the questions and answers at the end of the presentation. So rather than raise your hand for a question, just put it in the chat. We'll go through those at the end. So because yeah, we'll go through those. It'll be easier. So an hour of CPD attributable to this webinar. So yeah, that's that. Next slide. So CIWEM, Royal Chartered Institution, professional body, charity. So we have got environmental emergency. So and we do have kind of podcasts and various things on there. So be good to look on the website if you're not already subscribed to some of those things. So they are very good. So yeah, if you're interested in membership, hopefully some of you are members already. The ones that aren't, you are welcome to join. So 1,000+ members across the world, so 89 nations, so UK being quite a big part of that. So and various other things got linked in with universities and things like that as well. So so yeah, so good organisation to get involved in, and various events that happen across the branches. So this is hosted by the East Midlands, West Midlands branch. So and yeah, we have lots of other events going on. So so that's that. Next slide. So I think we're off to Howard. One thing that I will kind of just mention before, we in East Midlands, we have got a site visit of Toton Sewage Works on the 24th of June, so next month. So so that's in like Nottinghamshire way. So seeing the capital project that's been going on there. So there are events going on. We hope to have one of Derby Canal later on in the year. So yeah, various bits and pieces going on. So do keep an eye out on the website on the events page. I think I'll hand you over to Ludwig now, I think, is the plan.
To Howard. Your turn first.
Hopefully you can all hear me. So we've been invited to give you a bit of an overview of the projects which we've been working on for Severn Trent at Itchen Bank, Ludlow and Frankton to do with the micropollutant removal in final effluent, and basically to improve the health of the rivers in Warwickshire and Shropshire. More recently, there was an opening, or should I say a ribbon cutting, where at Ludlow, where we were invited to attend, of course, and Wilf, who you can see from Severn Trent, gave an address. The BBC were involved, and basically it was just to do more of a PR exercise to explain what Severn Trent have been doing and what we have been trying to achieve. So Severn Trent were pioneering. When we talk about these plants, we're talking about them as a pilot plant, but in point of fact, they're actually testing the full flow. Full flow will go through these. So where normally piloting will start with the lab test, as you can see on here, and then from there you would go into a more live project, probably 7 to 10 meter cubed an hour. So these are actually very large pilot plants. And we've already been told by the Environmental Agency that they're interested in the results that we're going to achieve on what we can achieve in this removal process using ozone. So this is a very idiot's guide, as we call it, to the process that's happening. And this one actually is at Frankton, so you can see from the labels that go through. We start in with the effluent which is being processed through, all the way through to where it goes through the TSR plant, through the backwash filters, and then on through to the ozone, where the ozone is bubbled in. I'll talk about more of that as we go through this presentation, but that's something that is not that unique just to Frankton, to be honest with you. On some they won't have TSR plants, but this one it actually does. So if we go into, I think the starting point has always been, where is the problem and what should we be addressing, and why has it come about? So the green recovery was a directive from the government where they realized that over all this time that we've actually polluted a lot of our rivers, and they're saying here that there's probably 90% of our rivers are actually polluted with not just effluent, it's actually from micropollutants, which we term the silent killer. They're the things you don't see. The sewage you see, this you don't see. So Severn Trent engaged with ourselves, Curio and Veolia, to design and build the micropollutant plants, basically in line with what was happening in Europe, because we had quite a lot. We'd had already 8 years experience in Switzerland on similar systems. So why is it important to have them? Well, of course, a lot of these would be pretty obvious, although we perhaps don't discuss them enough. You know, the healthy rivers support a really good ecosystem, biodiversity, communities, and the communities, the people are using it to swim, to boat, to fish. So healthy rivers for health and well-being. During the pandemic, there was a really big issue where people were actually using the rivers for swimming and a lot more sports. And they were actually getting a lot of gastric problems. So the cost actually of having unhealthy rivers actually is really, really quite high. So of course, public pressure now, and I think we're all pretty fully aware. We as the water industries are in the news on quite a regular basis. And of course, the majority at the moment is to do with sewerage and to the overspills and outspills, etc. But it's actually coming more and more prevalent because it's in the news more. So the wider economic and social benefits of having clean rivers is quite now in the public eyes, and growing awareness, of course. So the demand is becoming more and more on the water companies to do something about it. So bathing water quality. So this is the directive that actually came out from the government. So the objectives was to have an investment program to deliver the specific improvements to try to obtain or get our rivers back to a healthy state. Meeting the biological standards, improving against chemicals. Now, when we say this meeting the biological actually standards, there are no regulations in place currently for micropollutant removals. We do it with pesticides, we do it with nitrates, etc., etc. So these rules and regulations and the standards will be coming. They are definitely following Europe. So the objectives of these projects, which were right from the onset, was really micropollutant reduction and disinfection. So, of course, to get to that point, we have to go through a design phase to understand what we need to do. So we proposed a solution using ozone, which is diffused into the system. The reason we used the ozone is because it's an absolute brilliant oxidization and element within it to remove micropollutants. And then there is actually no byproducts after this part of the process, because the oxygen, the ozone actually reverts back to oxygen, so we don't have residuals within the water traces going back into the rivers. So considerations that we had to make in this, we had to understand, first of all, flow to be treated. And already we knew that Ludlow was in the region of 500 meter cubed an hour. Itchen Bank pretty much the same, and Frankton was a lot lower at 7. So we were designing systems with quite a range of flows in there, and these are peak flows. And as you'll probably be aware, there are extremities where you have bad weather flows, so we have a lot more than peaks to handle. And then there's the parts when we have quite low flows through there. So taking that into account to do the design was quite significant. And the properties of the water being treated. And then, of course, we had to look at it and say, what would be the consent of the parameters? What do we target? How much are we going to remove? And what kind of systems do we need to design to be able to take into account all of these different parameters? So the calculation was on the right of the screen, so you see it was quite intense. Using ozone in wastewater, you're faced with a couple of issues. One of the main issues is if you have too high concentration or dose of ozone, the risk of forming bromates is really quite high. So you have to design a system to try to mitigate that. So you need as low a dose as possible, but you need a dose adequate enough to do the job that you need it to do the oxidization. So the way that we designed this, or tried to mitigate this through our design, was to introduce the ozone at 2 different stages, and then to diffuse it in and to control the dosage from the beginning so that measuring at the beginning of the process and at the end of the process, so that you optimize the dosing points, but you mitigate the risk of forming bromates. So I guess it would be good to say a few things about micropollutants. I mean, what are they basically? What are they? So they're synthetic substances that originate from I have a real problem with this. Anthropogenic activities appear in small concentrations. Less than several micropollutants actually per litre are in our natural waters. Industrial, we get them from industrial, chemicals, pesticide, pharmaceutical, and harmonious, which of course is domestic. I guess the problem we're going to be faced with anyway, as of today, we understand the micropollutants that are actually existent and actually are needed to be treated. But this is going to be a moving target. As we speak, we know already that more pharmaceuticals are being developed for people to have longer life. So a lot of these, the contaminants actually are emerging concerns. So when we design anything, we have to design it to future-proof, to understand. So the starting point of this design was actually just using ozone. Since introducing the ozone systems that we have, other treatments actually are now going to become more useful, and we need to design into this system. So again, we'll talk about it in a little while. in this presentation the opportunities that actually are going to be available to us to not have one process, but to introduce several processes. So you can see from here the emerging. So on the right hand side of the screen, these are all of the different compounds, pharmaceuticals, personal. They come from personal care. They're industrial. They're domestic. So quite a broad range to deal with. So micropollutants and CEs in the water cycle. It'd be interesting just to have a quick look at this to see how we have to consider these and the concentrations they have. So micropollutant traces range from nanograms to micrograms. CEs more commonly are measured in nanograms. So again, gives more complexities to designing the system to be able to treat them. So again, I'm sure most of you are aware of this and the sources of them. So there's a lot. We talk about micropollutants, but when you look at it in this kind of level, there's 110,000 registered substances in Europe, which is a huge amount that are actually getting in through to our wastewater system. And there's a 200 to about 1,000 being identified more each year. And these are built up from the chemical products, pharmaceutical, cosmetic products, heavy metals. So they just don't exist as one item. Again, going back to designing systems to be able to eradicate or to remove these is quite a complex process. So why use ozone? Ozone actually has been used in water treatment very widely for a number of years. In fact, we were building plants in the UK on drinking water some 20 years ago. And they're great for killing algae, oxidization of micropollutants, oxidization of iron and manganese, which is quite well the process known in drinking water. The bacterial disinfection improves taste and odor. A lot of the water plants were we used actually for the colour and odour. Colour in Scotland definitely, and odour in sort of the north of England, and of course pesticide removal. So we actually have been dealing with micropollutants for some 20 years because pesticides actually is a micropollutant. So ozone, the reactivity of the micropollutants. So it's the nature of the target of the compounds, the speed of reactivity with ozone. One of the issues we're actually faced with, the suite of micropollutants that we are trying to treat will all react at different times. So you get some which will oxidize very relatively quickly. You'll get some which actually need a longer contact time, and then you've got some which are a bit more like the benzenes.
So we got a bit of a technical issue, so hopefully Howard will join back again. He looked like he was taking his headphones off, so hopefully he'll be back very shortly.
Okay, I will get back to where Howard was. Let's see when he dials in. Let me just get the screen up and share from there. 1 second. This one should be it. Okay, I think we were here with the ozone reactivity and micropollutant removal, obviously with the cocktail mix. Let me just move it over. What happened now? Andrew, I see you. What happened here? Let me just do that again. Sorry, now we have some issues.
I can see your screen and I can hear your voice.
Okay, good. There we are. Since we have a cocktail, we need to look at the individual micropollutant contaminants regarding their speed of reactivity with ozone, then how we diffuse, how we get the ozone gas into the effluent, and how much reaction time do we give it to each component. And then there's obviously an impact to the downstream environment. What have we actually oxidized? How is that treated? So the overall ozone system approach is very carefully to be evaluated. And there are different means of injecting ozone actually into the effluents. We have very fast reaction time when we use very small bubbles. So that is fine bubble diffusion. But we introduced this against sufficient hydraulic head. So typically, as you have seen at the slides from Howard, we have large columns where we have a water layer of 5-6 meters. Then the reaction time, how long are the micropollutants being exposed to ozone? That has that we are talking minutes. We're not talking hours. And minutes for some fast reacting components, we can even do that in seconds. But the typical reaction time, if it's ozone only as an oxidant, we're talking in the range of 10 to 20 minutes. And obviously that we have to look at the hydraulic depth again and the water pressure. If we have slow reactions, then we have to make sure that the ozone is dissolved consistently in the effluent, and again have sufficient hydraulic retention time without dead legs, etc., in the reaction tank. So there is quite a few things to be taken care of when you look at the ozone treatment process. Somewhere we need a gas containing oxygen that is being part of the oxygen is converted into ozone. Typically, it's LOX or liquid oxygen or compressed air. If there is a LOX, which is basically pure oxygen, you want to add a bit of nitrogen for the reaction with ozone. So for having the ozone being generated stable. The ozone itself is generated in a separate reactor outside of the effluent, obviously, that is powered by electricity, so you need a power supply unit. The generation of ozone produces heat, which needs to be taken away, otherwise we lose the ozone again, so cooling water is needed, and obviously flow and pressure control. Then once we have the ozone, and it's never 100% ozone, you're talking a percentage of ozone in the gas flow, let's say 10%. So this 10% ozone containing gas, the rest is oxygen from the LOX tank. We need to be put into the contacting vessels, and we need to have a diffusion system. You can't guarantee that 100% of your ozone is being consumed by the effluents, so you always have to have a safety measure of taking care of the excess ozone. That is an ozone destruct unit, so you need off-gas pipework and ozone destructors. And in the end, you need to control the whole thing. How much ozone do we actually add, which is not just a matter of flow rate, but you want to measure residual ozone. And one interesting aspect that came out of the work in Europe is the measurement of the UV absorbance before and after the ozone addition, because the ozone attacks the double bonds, which are typically the micropollutants, and that means with the delta of the UV absorbance, you can actually measure the performance and control the ozone amounts that you are putting in. So here you can see this graphically, what I've described regarding the setup, which is also the setup for Severn Trent. we have the air inlet for the instrument air feed and the nitrogen addition. So air is added to the LOX tank, so the oxygen feed gas, to provide the nitrogen amount that is needed for a stable reaction. We have the two generators here in violet, which also receive cooling water. From there, the ozone gas goes into the contact tanks. The off gas is collected from the contact tanks to be treated in the ozone destruction units in bright red, and the treated effluent goes out after its retention time passing through the contact tanks. And in orange, over to the left, there is the control system and power station. So, well, okay, Howard here is not back yet, right? So I continue, because Howard, you can jump in any time, because I'm actually representing the partner of Curio, Veolia. So that's really Howard's Curio story here more, because they've headquartered now in the Cranfield campus, where there are more trials going on with Cranfield University. And Curio actually will be putting up multiple pilots to test the combination of multiple micropollutant processes to be able to flexibly test subject to the requirements of the utilities and also to upcoming regulations that may be faced in the UK. So ozone is obviously part of this one. There is granular activated carbon and activated carbon, advanced oxidation with also UV, MBBR filtration. I will explain that also in full-scale plants a bit later. So this will be accompanied by laboratory scale trials, so that whoever wants to really test its effluent, his or her effluent, has a very good means what is the best combination regarding CAPEX and OPEX and carbon footprint for the particular effluent they want to test. Because now I can actually paint a bit larger picture here. We've talked about the three sites at Severn Trent. Micropollutant treatment in wastewater Europe has actually regulatory-wise started in Switzerland. So Switzerland put up a rule in 2016 which obliges the selected wastewater treatment plants to reduce micropollutants by 80% of the incoming charge. And the first plants were put in actually at that time, but there were multiple pilot demonstrations before that and still ongoing. And I think Switzerland is a bit the mecca of people wanting to understand how micropollutant processes work. I'm actually currently in Switzerland at our headquarters here, and where we have several sites which have seen multiple visitors out of Europe and out overseas to really see that. From there, it has grown into Germany, France, Scandinavia, and the Netherlands, because it was clear that the European Union also will regulate this, and the Urban Wastewater Directive now requires micropollutant removal for European Union sites as well. This is shown on this slide, what that means. So by the large plants, with a population equivalent of more than 150,000, will need to have this so-called fourth treatment step, and 100% by the end of 2045, which is 20 years from now. But as you can imagine, with all the planning cycles, investment cycles, etc., that is 20 years can quickly pass by, but it already has started. By 2033, 20% of the big plants need to have this fourth treatment step. The smaller plants, that's not all of them, but those that discharge into, let's say, declared environments that would have a risk if it's untreated. So sensitive environments, there you also need to start treating, and that means also smaller plants will see the fourth treatment step. And there are, as you could see from the pilot setup from Curio, there is definitely a lot of different treatment processes. I will just highlight a few here. Let me just open this up. So you have, for example, powder activated carbon added as an adsorptive mean. We can work with ozone plus a sun filter or an MBBR downstream. And if you go even further by upgrading your biology from, let's say, conventional activated sludge or even older technologies, and we work with a MBR system. One solution that has started to see full-scale operations is a PAC-MBR combination. I'll go into some details now in the next slides to give you a more technical overview. So powder activated carbon can be added into a contact chamber where the secondary treated effluent is received. You need to obviously mix it there, and then afterwards you need to take the powder activated carbon out again. In this case, this would be with accelerated clarifiltration, where also a microsand is being added for better settlement. So some kind of retainer. I also know plants which use cloth filtration or other things usually needs to be added to make sure that the powder activated carbon, which has absorbed the microorganisms, don't end up in the clarified water. Obviously, a constant add-on of PAC into the system, but a very, let's say, simple operation after all. Ozone is, as Howard has already started to describe, been used in drinking water and wastewater for a long time for treatment of pesticides, odor, and taste. So that's not something new. The setup is also quite well known. You typically have a contact chamber as shown here, where you use, first in this example, the first and the third chamber to bubble in the ozone with a certain retention time in this contact chamber. In order to make sure that no transformation products are being released to the environment, typically a biological filtration, in this case, in this example, a sun filter is added. With sun filter, you have some backwash as well. That system is actually one of the, let's say, most used ones in the oxidative mechanisms. Imagine the sun filter is replaced by a mixed bed biofilm reactor, by an MBBR. Then actually you can get rid of the backwash water. So actually OPEX costs are being reduced, and typically an MBBR is also having a smaller footprint than sun filtration. So that's quite a neat combination using ozone and MBBR, which is a trade. Veolia has a Xeno trademark for their specific MBBR solution, with also references in Central Europe on a combination with ozone. And this biological step actually, so this is no longer a filter, this is now a biological step, also adds even to some extent with the degradation of micropollutants as well, with the speciality of the microorganisms growing on the fixed film. Big aspect though, no backwash, and that means lower operating costs. You could also replace the biological sun filtration or MBBR with a granular activated carbon filtration step. This schematic is maybe a bit misleading, because if you do ozone and activated carbon as a combination, you have two mechanisms that will treat micropollutants. You have the oxidative effect of ozone, and the adsorptive effect of granular activated carbon, which means you can balance out how much ozone do you really need. You will reduce the amount of ozone compared to a treatment with MBBR or sun filter by, I would say, approximately 2/3. So you can really save on the ozone operating costs and ozone size. You also can reduce the retention time a lot, because in the end, ozone would then only be used for the fast-acting compounds and partially oxidize, and GAC will do the polishing and absorptive of all the things that are not oxidized. There are some great references, especially in Switzerland. The GAC filter bed cycles, I think that it has survived now 60,000 bed volumes already. So I think 5 years of operation without having the GAC replacement due to the ozone add-on before. So it's actually quite an interesting combination. Obviously, GAC has also the capabilities of treating PFAS. And that means there's a bit more robustness in this combination. Last but not least, and I think we have loads of time for Q&A happening, which hopefully has Howard back with us. A completely different approach. If you also want to upgrade your biological treatment step. So if for intensification, for further phosphate and nitrogen removal, you want to go to a MBR step, then what has been already tested and put into the field is a PAC MBR combination, because the MBR will obviously act like a filter, and the powder activated carbon will not end in the effluent. So this is quite a compact concept. Obviously, it requires an MBR as the biological step, so that's something that will be subject to biological needs, not micropollutant needs, but a very interesting combination. By the way, ozone after MBR is also something that is being tested right now, because the amount of ozone needed after MBR is obviously less than before a sun filter or MBBR. So again, we are reducing the amount of ozone. We are therefore also reducing the risk of byproduct formation. The most famous one is bromate, only happening at high bromide concentrations and high ozone dose rates. Whatever you can do to reduce the ozone dose rate, like MBR or activated carbon, helps to minimize that. But again, MBR means we want to upgrade the biology, and then we can think of a different concept for the micropollutants pathway. Okay, then let me shift over to the final slides. 1 second, they are here, because now we can go to this one. And I think we can open up for any questions that I can answer, because I think Howard has not rejoined. At least I haven't heard him yet.
I think Howard's back, I think, now.
Okay,
yeah,
cool.
got back, yeah.
Okay. So Howard, I carried through the presentation then.
I did, yeah. I got back and saw some of it. Thank you.
Okay,
yeah,
good.
really good, yeah.
Yeah.
Is there anything you want to add, Howard, and then I'll go into the questions and answers?
No, I think listening to what the carry on from Ludwig was absolutely fine. It's you know, I think basically the message from this session should be, this is the start of the journey. This is not anything but that, and there's a lot more research needed and required. Because at the end of the day, you could build a plant that is so super, it gets rid of everything, but you can't afford to run it. So we're always going to be faced with what can we remove and what are going to be the costs of doing that removal, because they're the barriers. I think there's a desire now to do that, and Severn Trent are leading the way with that. 100%. So now the journey starts.
Yeah, perfect. Yeah, it was interesting to see the timelines. I think 2033 for 20% of the larger works to have that. I guess a question from me to start off really would be the obviously you've got this end process of dealing with the micropollutants. I'm guessing in Switzerland and Germany, being EU, there's rules about the formation of micropollutants in some of the chemicals, shower gels, and obviously you can't get rid of all of them, so people will put antibiotics and stuff down the toilet. But how do you address it at source to remove the need, and what's going on in Europe to try and do that?
I think one is, first of all, financial pressure on the polluter pays principle. That's obviously all this needs to be financed somehow, and that means the producers of the original micropollutants are being made responsible financially for what's going on there, which makes them rethinking how they are marketing and how they are addressing the way that their products are being handled. I think the overall, since this is now a much bigger topic than before the release of the Urban Wastewater Directive modifications, people are getting much more aware of what's going on. So I would hope that if somebody puts diclofenac now on something that hurts, afterwards you don't wash your hands, you wipe it off with a cloth, and don't pollute the wastewater with diclofenac, because that's one of the major issues. And those things are now happening with the plants in the big urban areas needing to upgrade. So they spend a lot of time educating the population about what kind of micropollutants they actually add to the waters.
Cool. Another question we got on again about doing this obviously kind of removes the micropollutants. Obviously there are some kind of trade-offs. So using the ozone production, quite energy intensive, I'm guessing. So you're solving one problem, but you're creating another environmental problem with that. And I guess the same question in a slightly different way is, how can you ensure the long-term safety of the substances introduced into the ozone treatment process? Will bromate not form over time despite the low quantities? So yeah, the energy and the bromate. So from a consequence point of view.
Yeah. Okay.
So on the energy, can you hear me okay?
Yep.
Yeah, okay. So on the energy side, that is quite correct. Producing ozone is not that energy efficient. However, by introducing other processes or treatments within that train allows us to have a far less arduous task of having higher quantities of ozone. So doing AOP to start the process using UV, you get two benefits. You can reduce the size of the ozone plant, and you also get a disinfection phase of that. And then using other treatments like the MBBR or GAC, you can then lower the size of the ozone plant, and that's what we're trying to do. We're trying to look at the optimizing the treatment trains, and we'll do that through the pilot planting.
Perfect. And then on the bromate.
On the bromate, yeah. So first of all, to explain, bromate is formed if we have excess ozone and a high concentration of bromide, or relatively high concentration of bromide. Okay. Obviously, bromide concentration mainly due to industrial discharges. So a typical just purely municipal wastewater without industry wouldn't have high bromide levels. But let's say in the Swiss plants, this has been also recognized. Okay, there are fluctuations. So you'll do your test first of all where you are over a certain period of time, and then determine if we are adding ozone, only, first of all, is there the risk of forming bromates? There are ways of mitigating with multiple ozone dose rates points. The main aspect, though, and that's coming back to what Howard was already saying with the energy, is let's lower the ozone concentration below its immediate ozone demand, so that we're addressing the fast reacting compounds like diclofenac, and use a combination with activated carbon. And then it is scientifically proven we are not forming any bromates. It's a very slow reaction, and if you only dose a little bit of ozone for the fast reacting compounds with a small retention time, that problem is avoided.
It is mitigated, yes.
Yeah. So it's something we are all, let's say, as I was saying, we are beginning of the journey. There are plants that are in operation for 10+ years, so there is experience, but it also is based upon they were built with what we knew 10 years ago. So now we can further optimize.
The O3 and the GAC, how much of the extended bed life or performance do you attribute to the absorption rather than biological activity? It's an easy one for you.
It's one, that's right. What kind of, to be frank, I don't know. That's let's say the extended bed life at Altenrhein, because they had a pilot running as well next to it, is definitely due to the there's still ozone in the water when it enters the activated carbon, and that has helped to keep the activated carbon absorptive. So it's not aging in a way that needs to be replaced.
In fact, Ludwig, the group, in drinking water, we always try to carry over on post-ozonation a small amount of residual ozone if it's going onto the active carbon beds, because it's been proven over the last 20 years that it helps the life expectancy of the GAC itself in between the regeneration of it. So that has been proven to be a fact that it works. It does work. In excess, it does not work because it gets rid of the biological side of it. But the case is we always try to keep a small residual, so we control the outlet to maintain that residual of probably less than 0.1 as a dose milligrams per litre.
Does ozone generate on site or transported from elsewhere?
No, it's
quite short.
Yeah, it is generated on site, and there's two ways of how we're doing it. So if you go to Itchen Bank and Ludlow, we're producing that using LOX, liquid oxygen. But at Frankton, because the flow is much smaller, being 70 meter cubed an hour, we're producing the ozone through our generator system using air. So it's actually produced through a silent barrier discharge in an ozone generator. So hence there's no storage. You use what you produce basically.
Cool. Someone's asked, I'd be interested to hear more about the specifics of the DBP management strategy built into the systems. See, this is an important issue when applying the O3 as part of water reuse configurations. Hopefully that means more to you than it does to me. The DBP.
Disinfection byproducts. Well, okay. If ozone as a disinfectant in this case, right? The biggest concern is typically bromate, and that is mitigated with how we have discussed with ozone concentration control, and obviously managing the right dose. there is, and then we're discharging into the rivers, so there is no chlorine added, which if there would be still THMs in the water, well, after ozone, obviously much less, then you could form further, if there would still be organics left, then you could create THMs, but that's not happening. So there is, except for the bromate issue, nothing that we need to really work on to mitigate.
Right.
Howard, would you see anything else that?
No, I agree entirely with that.
Cool. And I think the last one, only other compounds or elements which have been identified which could present similar risks to bromide depending on the composition of effluent being treated.
Maybe I give first of all an answer which doesn't answer this one, but if anybody considers designing a fourth treatment step with ozone, whether in combination with activated carbon or something else, nitrite and DOC should be measured, because these are the two, let's say, they don't form. We don't form byproducts there, but they are the ozone consumers, so to say.
Yes.
Right. So that without those two values, if somebody says, "Oh, I want something to be designed," Howard and I would be second guessing how big the ozone system would need to be. But with nitrite and the DOC value, or TOC value, sorry, total organic carbon, we can fairly safely predict what is needed for an ozone dose, depending on the follow-up step, whether a sun filter or MBBR or activated carbon. So I think the only other aspect is if there is any kind of NDMA formation possible, but that is something that I've only seen in combination in the US with potable reuse work. So something where again, this pathway with high dose rates on a completely different level for disinfection, this is not a pathway that we have here right now for the fourth treatment step. Cool,
perfect. I think that probably takes us to the end of the session. So just want to thank you guys for the presentation and obviously your knowledge of the industry. It's really good to see kind of this kind of element of kind of water quality. So we're doing lots on spills, and this is kind of the future and the next steps. So so it's good to see this, and obviously over the next kind of few years, it's going to kind of massively kind of increase with more research. So the test beds you got at Cranfield and various other bits. So yeah, so really amazing kind of to hear all the work. So thank you very much.
Yeah, very welcome. Thank you for the invite, Andrew and Barbara.
Cheers. Thank you all.
Okay. Thank you very much. Have a nice day.